Welcome to this module on Advanced Mathematical Economics. Advanced Mathematical Economics is not just about applying mathematics to economic questions, it is about building a precise, logical, and rigorous foundation for economic reasoning. The methods we explore will allow you to formulate economic problems in a mathematical structure, identify the key relationships and constraints in an economic environment, analyze optimal decisions and equilibria under various assumptions, predict how systems respond to changes in parameters, policies, or external shocks. Our approach in this module will be both theoretical and applied. We will begin with the mathematical foundations necessary to navigate the rest of the course. We will then move on to optimization techniques, both unconstrained and constrained, before applying these tools to core topics in consumer and producer theory. Finally, we will study the role of convexity and concavity, concepts that underpin much of economic optimization. By the end of this module, you should be able to interpret economic problems in mathematical form, apply optimization techniques to find solutions, understand the role of comparative statistics in analyzing policy effects, recognize how curvature properties of functions influence economic outcomes. 2. Mathematical foundations. Before we can analyze sophisticated economic problems, we must ensure a common foundation in mathematical concepts that are central to the discipline. 2.1 Functions and mappings. In economics, functions are the building blocks of theory. A function is a rule that assigns to every element in one set a unique element in another set. For example, a consumer's demand function assigns a quantity demanded to each possible price. The set from which inputs are taken is the domain, and the set of possible outputs is the range. Functions can be linear or nonlinear. Linear functions have constant rates of change, while nonlinear ones have variable rates of change. In economics, nonlinear relationships are more common, as most economic behaviors exhibit diminishing returns, increasing returns, or other nonlinear effects. 2.2 Limits and continuity. Economic reasoning often requires us to think about what happens as variables approach certain values. For example, as the price of a good approaches zero, what happens to the quantity demanded? This requires the concept of limits. The limit of a function describes the value that the function approaches as its input approaches a certain point. Continuity is another essential concept. A function is continuous if small changes in the input lead to small changes in the output. In economics, continuity is often assumed because it reflects the idea that preferences, production technologies, and other economic relationships change smoothly rather than abruptly. 2.3 Differentiation. Differentiation is the process of finding the rate at which one variable changes with respect to another. In economics, this is crucial for understanding marginal concepts. The derivative of a function at a point tells us how fast the output is changing at that point. For instance, the derivative of a cost function with respect to output is the marginal cost. The derivative of a utility function with respect to consumption is the marginal utility. Higher-order derivatives are also important. The second derivative can tell us about curvature, whether a function is concave or convex, which has important implications for optimization. 2.4 Integration. Integration is the reverse of differentiation and is used to find the total effect from marginal quantities. For example, if we know the marginal cost function, we can integrate it to find the total cost function. Integration is also used in welfare economics to measure total surplus or the area under a demand curve. In this course, integration will also play a role in dynamic analysis when we study the accumulation of capital, resource depletion, and intertemporal optimization. 3. Economic optimization without constraints. Many economic problems involve finding the maximum or minimum value of a function. For example, a firm might want to maximize profit given a certain production function, or a consumer might want to maximize utility from a bundle of goods. In unconstrained optimization, the decision maker is free to choose any value of the decision variable. The general approach is: identify the objective function, such as profit, utility, or cost. Differentiate the function with respect to the choice variable. Set the derivative to 0 to find critical points. Determine whether these points correspond to maxima or minima using curvature properties. Economic interpretation is crucial. A maximum of a utility function represents the highest satisfaction a consumer can get given their choice set, while a minimum of a cost function might represent the least cost needed to produce a given output. 4. Economic optimization with constraints. In reality, most economic agents operate under constraints, budgets, production capacities, legal restrictions, or resource limitations. This leads us to constraint optimization. 4.1 Equality constraints. Equality constraints specify that some combination of variables must exactly match a particular value. For example, in consumer theory, the budget constraint states that the value of a consumption bundle must equal the consumer's income. The method for solving such problems often involves introducing a Lagrange multiplier, which represents the shadow price or the marginal value of relaxing the constraint. 4.2 Inequality constraints. Inequality constraints specify that variables must satisfy less than or equal to, or greater than or equal to, conditions. For example, a firm may be restricted to produce no more than a certain emission level. These problems can be handled using the Kuhn-Tucker conditions, which extend the Lagrange multiplier method to account for situations where constraints may not bind. 5. Comparative statics. Comparative statics is the study of how changes in parameters affect the optimal solution of an economic problem. For example, how does a change in the price of a good affect the quantity demanded? How does an increase in wages affect the optimal labor input chosen by a firm? The basic steps involve deriving the first-order conditions for the problem, differentiating these conditions with respect to the parameter of interest, interpreting the sign and magnitude of the resulting expressions. Comparative statics is a central tool for policy analysis, as it allows economists to predict how changes in the economic environment will influence behavior. 6. Convexity and concavity in economics. Convexity and concavity are properties of functions that have profound implications in economics. A function is concave if the line segment between any 2 points on its graph lies below or on the graph. Concave functions represent diminishing marginal returns, which is common in production and utility functions. A function is convex if the line segment between any 2 points lies above or on the graph. Convex sets of feasible options are essential for well-behaved optimization problems. In consumer theory, convex preferences ensure that consumers prefer averages to extremes, leading to smooth, well-defined demand functions. In production theory, concavity of the production function ensures that cost minimization and profit maximization problems have unique solutions. Closing of Module 1. We have now established the mathematical foundations and core optimization techniques that will serve as the backbone for everything that follows. You should now be able to understand the importance of limits, continuity, differentiation, and integration in economics. Apply both unconstrained and constrained optimization methods to economic problems. Conduct comparative statics to analyze policy changes. Interpret curvature properties and their implications for optimization.